All righty. Well, so got all my stubby little pieces of chalk because I dropped that thing again. Okay, we are talking about regression and so let me just start this with our hypothesis test versus modeling. Okay, because regression can really do a couple different things for us. I actually use least squares in regression quite a bit without ever thinking about the hypothesis test that goes with it. Okay, because it's just it's a nice tool to fit models to data, and often I'm not really interested in whether I'm trying to determine if there's a dependency or not. I know there's a dependency going on. That's why I'm trying to do the model. So there are those two aspects to the hypothesis test versus the model. And we could go into all the calculation and so forth that go into coming up with the model and the p-value and all that, but I don't see a reason to do so. I mean, it's just a bunch of either algebra or calculus or something like that you're doing to get there. I don't think it's that enlightening as far as what it is we're trying to do with it. And so the hypothesis test side, our null hypothesis, now again, one way to state the null hypothesis for any of these tests we're doing is that the two variables we're looking at are independent. Okay, that is always our null hypothesis when we're dealing with two variables, is they're independent. Okay, but, well, what does that mean for this? And in particular, what this model is asking or stating in the null hypothesis is that the slope of the regression line, so, this is where the model and the hypothesis test are very linked, because we have to get the model, we have to get the slope of the regression line is equal to 0. Okay, but that's the independence part of it again, because if the slope is 0, my data probably looks something like that. And again, from a prediction point of view, I really wouldn't be predicting anything differently whether I'm here with X, there with X, or there. I'm going to predict pretty much the same thing. Oh, that's independence. And so in H0, the slope of that regression line is 0. The alternate, well, it's not 0. The slope is not equal to 0. And again, in a small picture here, if you have data that kind of follows some trend like that, then again, if I'm down here, well, I'm going to predict an answer somewhere in there. But if I'm out here for my X value, I'm going to predict an answer up there somewhere. Okay, so if I change where X is, my value of X, where I'm looking, then I change my prediction. Dependency. Okay, so it makes sense that those might be for something like this, the null and alternate hypothesis. Okay, so then from this, right, we take our data, we throw it into something, this linest command or linest command, or however somebody wants to pronounce it. I don't know how Microsoft, who first coined the term, I guess, pronounces it. At least I think they did. Of course, they stole some stuff from other users, you know, so I don't know. They may not have. But, you know, it's the command is linest or linest. Now, it's probably linest because it's linear estimation. So it's probably linest, but that's our command that we use within Excel or some other spreadsheet. They all use the same name. And again, you know, well, I know what's going on inside it, but I mean, we don't need to know. Most importantly, for the hypothesis test, it produces a p-value, and that is what matters for our null hypothesis and alternate hypothesis, right? So p-value, if that p-value is greater than 0.05, then you know, we fail to reject our null hypothesis, H0. And again, that's the best way to state it, or we don't have enough evidence to go with the alternate hypothesis, you know, something along those lines, but it's sort of a negative statement about that null hypothesis. Okay, we fail to reject it because that's probably what we were hoping to do. Then, you know, if our p-value is less than 0.05, okay, we reject H0. And again, then, you know, we get to say something positive, like there's strong evidence that the alternate hypothesis is true. Okay, something like that. Okay, that's the hypothesis test part. Okay, now the modeling part, it's not as big a deal in this this chapter as it is in next chapter. Okay, so next chapter, the modeling part really comes into play with trying to determine our results for a hypothesis test. Because in the next chapter, we're going to toss in all our confounding variables. See, so far, right, when we've talked about confounding variables, the only way we've known how to handle it was to separate it out. Right? That's what you did in Module 4, right? Is we separated it by the confounding variable. We couldn't just throw it all together. Well, with regression, we're going to find out we can probably just throw much of this stuff all together. But then, when you do, the modeling part does become important. So, you know, in this chapter, the model's not as important, but I think it's important to determine or to understand, yeah, there's these different aspects of what we're doing. And so the model, what it's trying to do is fit something like y equal bx plus a. Okay, again, I'll go with the b or beta and an a or alpha as opposed to our usual mx plus b kind of thing. So we've got that model. It's trying to fit that model, and it uses this least squares criterion. So, you know, as it tries to fit this model, it it looks for a model that minimizes the sum of those distances squared. Okay, that's the least squares idea. But in doing so, it produces some numbers that are actually quite useful to us. And now you got to be a little careful. I'm going to talk about goodness of fit, but this is not the chi-square goodness of fit test. One can work with the chi-square goodness of fit test to do some things, but that's not what this is talking about. So we can look at our goodness of linear fit with R and R squared. Okay? What those tell us, and they really are just that, I mean, one's a number that we can compute. Actually, we'll compute R squared. But you can compute either R or R squared. R is our correlation coefficient. Okay, so R, well, let's say this, between -1 and 1 is the correlation coefficient. Okay, so now the weird thing with the R here is between -1 and 1, but actually either -1 or 1 are great numbers to get. 0's not, okay, from a model point of view. So the closer we are to either -1 or 1 with R, the better our data fit the model. Now how are they doing this? Well, if they really do have a pretty linear relationship and so forth, then for R, what you tend to see is, if I have data that are pretty tight to the line, okay, so if that's the case, then if we see something like that, where these are very close, these deviations from the line are very small, then here, in this case, since B is greater than 0, the slope, okay, the slope is greater than 0, we're going to see R is greater than 0 and near 1. Okay, because it's really tight. So when you get numbers close to 1, things are very tight to the line. Similarly, if your data were coming down like this, and again, they were pretty close to the line, so B is negative though, so you got a negative slope, then R would be also negative, and near -1. And the closer you are to just having a big old cloud of points, okay, that you would probably see a slope of 0. We'll look at that in a minute, but you wouldn't necessarily have to. You could have this big cloud and have it going up a bit or down a bit. But you have something like this, and R is near 0. Okay? But yeah, just to make sure you realize it doesn't have to be a 0 slope, is that, I could have data like this, where, yeah, there's some space here and there's a little space there, but it's really wide, okay? And maybe that line goes like that. Again, R is near 0. Okay, the R has to do with how well the data fit. And I just noticed I'm using a lowercase r here, uppercase R there. Different authors use different cases. Okay, now to make that a little more precise, that's where R squared comes in. So R squared tells us the proportion of the variation in Y explained by the model. And so really explained by the slope is what it comes down to. Because in the model, and I think I mentioned this last week, is that, now it's not the y-intercept itself, but the line that we pick is always based on the average of the x's and the average of the y's. So no matter what slope we pick, we always know the line goes through a point that is the average of the x's and the average of the y's. So, so really, this variation is going to be explained by the slope, really, when it comes down to the model. So if you look here, right, you would expect, see, r squared is near 1, or sorry, if r is near 1, when you square it, you'll get a number nearer to 1. And again, see, things are really tight to the line. You know, it's explaining getting this data very close to that, so the model is really quite good. So if you have this r squared that is like 0.8, oh, well then that says 80% of the variation I see in all these y values is actually explained by that line right there. Whereas, if you see an r squared down around 0.2, well, that says that only about 20%. So you may have a slope like this, or you may not have much of a slope at all. But as you look at this, see, I see all that variation from there to there. Well, as I move along the line, a little bit of it is explained because, yeah, sure, that cloud is heading up that way. But there's still a whole lot of variation around that line. So I might tell you I'm out here, which would say, oh yeah, certainly, you know, try to pick a number that's more in this range. But that's still a big range, right? So it helps, this model helps me pick, but not near as much as this model would, you know, with data like this. You know, these are almost right on. And so if I knew I was out here and I picked something, you know, in that area, yeah, I wouldn't be too far off. But here, I might still be quite far off of whatever happens in trying to predict that data. So the r squared is what we'll look at, and we want, you know, we're hoping from a modeling aspect to have an r squared very close to 1, okay, because it's, well, so 0 less than or equal to r squared, less than or equal to 1, because we're squaring it, so it can't be negative. And if I got points exactly on the line, then I would get a 1, or 100% of the variation in the y is explained by the model. Okay, so that's the differences. So we've got these two things here. We've got a p-value and we've got this thing called r squared. And they're very related. They are very related, but they are not surrogates for each other. So this project talks about surrogates. If I know something has a low r squared, it does not mean that my p-value is big or something like that. So again, right, a low r squared would mean my data are very spread out. And so it might mean, like up here, that things look pretty independent. But they don't have to, okay? Because the r squared, if I have a big enough spread in my data, yeah, my r squared is not going to be very big. It just can't be, because there's just so much spread in the data. But that data still may have a very definite either upward or downward trend to it. And so in that case, there's definitely a dependency. So, well, it was over here. My hypothesis test, my p-value will probably be still quite small. But the r squared will also be small, which is not what you'd want. Okay, so you just have to realize these are related, but they are actually two different items that two different quantities that we're looking at. Okay. So let me go back then at this point. Anybody have questions over anything? I just wanted to get that started with that. Make sure that we're thinking about the fact that p-value and r squared are not interchangeable. Okay. But any questions, project, anything like that? I'll talk a little bit about the project, but okay. All righty then. Yeah, let's look at the project a little bit with this linest command, and there's really not that much to the project. I can do a spoiler, right? I can do a spoiler alert and say, hey, you're going to analyze it with 3 different methods. They are all going to show a tiny, tiny p-value. And so the alternate hypothesis is the answer every single time. But that's part of the point, okay, is that we're going to take this data, we're going to look at it slightly differently, use first least squares, then analysis of variance, and then chi-square. And they're pretty much going to all give the same answer, which they should. Okay, because it's based on the same data and they're all asking essentially the same question. Okay, but that's the point. Okay, is that everything we're doing in here is the same old thing every time. And so let's see if I can find it. This one. Okay. So in this project, first you're asked to just enter labels and data and so forth. So now, where it says divide by 0 and divide by 0, that one and that one, yeah, I jumped ahead a little bit, okay, because it actually has you do the other stuff first. But as we look at it, most of what you do on this project is just entering labels and that sort of thing, as far as the least squares analysis. Okay, so I wanted to show you here, I have videos where I do this and so forth. This is the template you're supposed to make, or, well, it's close to it. I don't think you have the alpha for confidence in there. That's a holdover from something else I had. And It doesn't hurt to remind yourself that, right, we tend to look at 0.05. So, you know, it's almost what you are supposed to do in part 1. So you've got all this stuff. Now, two very important things. The first, this one is the second most important thing. I think it's the second most important thing anyway. When you go to enter the command, you need to highlight all 10 spaces where it's going to go. Okay, if you don't highlight it, it doesn't fill in there. All right, so this linS command, and you know, it's the Y data. Now that's also something kind of weird. You know, it wants the Y data first, then the X data. Then it wants a 1 and a 1. Now the first one is for a Y-intercept, not forcing it to be 1, but just forcing it to look for a Y-intercept other than 0. And then this, the second one, is for full output, to get all the numbers. So, you know, the 1 and the 1, pretty much with stuff we do, we would almost always just put those in. So it doesn't take much, but you have to highlight all 10 spaces. And it's 5 rows by 2 columns. And so you do that then without clicking again. And that, at least speaking from my own experience, that actually kind of took me a little while as far as motor memory kind of stuff, is that, you know, I would highlight it, and then I would go, okay, I want to put something right there, so I'd click on it. And the highlighting goes away, right? So you have to kind of make sure that, okay, you highlight it, and then you just let it alone, and you start typing. And so I say equals linS, the open parenthesis in there. On mine, it's telling me get the data for the Y first, and then the data for the X. So I go here, get the Y data, and I highlight that. And then a comma, and do the X data, and I highlight that. And then the 1 and the 1. Whoops. And close that parenthesis. Now, so that was the second most important thing, was the highlighting. The most important thing is, this is a vector command. Now, I can't show both of these things at once, so I am writing. I'll switch back to the board in a minute, both for the recording and anybody remotely coming in. But this is a vector command. Okay, and by vector command, that's just simply saying it's going to fill in more than one space at a time. And so, for whatever reason, in all these spreadsheets, to do a vector command, you typically have to hold the control key down and the shift key down, both of those at the same time, so control and shift. And what I do is I hold those down with one hand, and then I hit enter while those are held down, and it fills in everything. Okay, so let me switch back real quickly just to show, you know, so what I wrote on the board was the line, the linS command with the Y data, the X data, and the 1s and the 1s, and then I pointed out it's a vector command. So that's what I had on there. Oh, wrong thing. Try this again. There we go. Okay. And so, you know, the important things that we want from this, well, we can look at the slope and the y-intercept, but you know, there's the slope. 0.74. And then we've got the standard error for the slope. Okay, now I'll switch back to the board for a second. What we want to do for that is, this is like other hypothesis tests. It's just going to run a t-test. Okay, so like our z-test, but it's in essence checking the null hypothesis. Is this number equal to 0 or not? Okay, is this average that it's trying to come up with equal to 0 or not? Well, remember when we did a t-test, we would make our t-statistic by taking our x bar minus our mu 0 divided by our standard error. Okay, that's what we did to compute that t-value to look up for a t-test. Or, you know, when you, so when we had the null hypothesis that the mean was this mu 0, and then we got this data. Right? So it's the same test. It's just doing that with its calculation. The thing is, though, our hypothesized number is 0. Okay? And our mean, the mean it's coming up with, is the slope. And so its t-value is the slope over the standard error. And so that's all it's doing. You know, that's all we're doing, is we're just saying, oh, well, what's the slope? What's the standard error? Divide them. That'll give us a t number. And so that's what you do with this. And in our case, that's 3.911. And we need degrees of freedom. The degrees of freedom are given right here. And that is always our number of data rows. So we had 10 minus 2. Now you can kind of intuitively go with the minus 2 because we've got a mean, or a slope and a y-intercept. Those are the two things that are taking away our degrees of freedom. And so it's 8 in this case. And we just look it up. So it's just that t-dist, and it says E8. Well, that's my t-statistic, the 3.9. And then F5, which is the 8, the degrees of freedom. And then the 2 for two-tailed test, right? We had our alternative is not equal to. So that's the two-sided test that we've been doing since very early on. And, okay, so I'm just going to hit enter so it's there again. And you see it's pretty small value. It's much less than 0.05, 0.004. Now, I knew that as soon as I saw the t number. If we look, oh, I didn't bring up the textbook. I'm not going to bring up the textbook, but in the textbook, pretty much if you look at the t-distribution, what you find is as long as this number here is less than about 2.5, I'm really sure we're going to get a small enough p-value. Okay, and you can see that just by looking up the t-distribution. Now, normally, that number would be around 2. Okay, why 2? 2 standard deviations, 95% of the data, alpha is 0.05. Okay, and actually, as your degrees of freedom go up, yeah, you're gonna definitely start getting smaller and smaller numbers. But for small data sets, it's even bigger than 2. So usually if that number is less than 2.5, I'm probably going to get a pretty small p-value. And definitely, if it's less than 2, I'll get a very small p-value. Well, very small. I mean, I know for a fact it's going to be less than 0.05 because that's our number, 1.96. Okay, that was that z-value that made our confidence interval, right? 95% confidence interval, 1.96. Okay, so when we're around 2, I know we've got things covered. But even for small data sets, it could be as big as 2.5, and it's probably going to be fine. So, you know, I was pretty sure it would be small, and yes, it is. Okay, so let's see. So that's what we need to be able to do. You know, just put our data in and go with that. Now, what I also want to do is show that R squared and p-value can be very, very different. Okay, so I'm going to do this with a really small data set. Now, notice when I get rid of that, I get errors, which may seem reasonable because, well, there's no data. Well, but here's the one problem. I call this a template, but in a lot of ways, every time you put new data in, if you've got a different number of rows, you have to redo that line, you know, the linest command. You just have to do it from scratch every time, equals linest, and do that, because as soon as I have rows missing, it gives me an error. And so, let's see, if I go 1, 2, 3, I think, and then here, 1, 2, 4. So just 3 data items. Now, this is part of the reason this is going to work out this way, but notice it's still giving me an error and I have data there. Okay, again, the reason is it's looking at spaces down below. So I have to highlight the whole thing. I'll backspace, but it's still highlighted. So now I can say equals linest. And I get my y values first, so the 1, 2, and the 4. Get my x values. And Control, Shift, and Enter. And notice R squared, 0.964. So better than 96% of the variation in the y values, that 1, 2, and 4, is explained by the model. Well, the slope's 1.5, and the intercept looks to be about -2/3. And so that would be y equals 1.5x minus 2/3. 96% of the variation. That is great. Real life data, if you get a 0.96 R squared, you are cooking on all burners, as they say. I mean, you're doing well. Okay, but look at the p-value, 0.12, 12%. Unfortunately, even though this model fits that well, the hypothesis test fails to reject the null hypothesis. They are not the same thing. P-value and R squared do not tell you the same thing. They're going to, on the whole, be kind of close or kind of reasonable. But you can get, actually it tends to happen much the other way. You can get a very small p-value, and yet your R squared is only like, 10 or 20% or something like that. So the model isn't fitting that great, but the hypothesis test says there is definitely a dependency going on here. It's just you've got the R squared, if it's really small, it just says you've just got a lot of variation no matter where you are in your independent variable, as in the x. Okay, your predictor variable. I should probably say that, not independent. So, okay. Questions on any of that? All right, so it's not as big a deal again in this chapter, but you want to lay the groundwork so that next chapter it doesn't seem so weird. Let me go back here. So actually, one nifty thing about the regression analysis is we can actually use it instead of an analysis of variance. Okay, so remember with analysis of variance, what you had was, you had a category A and a category B, say, something like that, right? And you had data, some x1, x2, x3, and so forth, or maybe I should call it A1, A2, A3, and so forth, and then B1, B2, B3, B4, and so forth. Right? We can analyze that, and the null hypothesis here was that the mean of A was equal to the mean of B. And the alternate, of course, was that they weren't equal. Okay, so that's what the p-value was telling us. How likely was it they could have been equal? And if it's really small, we don't believe it. Okay, that was analysis of variance. Well, we can actually do that we can analyze this case with the two categories or two levels of a categorical variable. We can actually put that into a linear regression. We just have to fool the linear regression, and we do it a particular way. And so with regression, we would still have, now here's x, here's y. So the response variable, it's still A1, A2, A3, down to something. And then B1, B2, B3, down to something. And what we do is, now it really doesn't matter which one of these we pick. Probably I'll pick the top one in this case. I'm going to put in a dummy variable. So this x is what we call a dummy. Okay, because it looks numerical, but it's not really. I mean, these are categories, right? And so all of these values down to here are 0, and all of these are 1s. And we put that into a regression, and it turns out we get the exact same sort of answers we get with the analysis of variance. Okay, so let's look at that with some sort of, I don't know if you really call it famous data or not. Is this the right data? Yeah. Okay, so here are some data from some irises, and somebody at one point measured 50 irises of actually 3 different species. I only have 2 different species here because we only know how to do 2 categories at this point with this. You can look at petal length, and so we've got the iris setosa, and then over here, so there's setosa, there's versicolor, and these are the petal lengths. Okay, now they're all in one column over in column B, and I've already put the dummy variable of 0s on the setosa, and see where I changed to versicolor, I changed that to 1s. Okay, so now if I highlight all that, should be 100 of them, and I copy it, and then I go back to our template, and I paste it in here. Okay, now, of course, I have to redo this, because, again, it gets very confused. And so this is my lin-s command, my y values. Now they start at B2, and actually I know that they go down to 101. And then I'm just going to type these in, A2 to A101, and then the 1 and the 1, and I'll do the Control-Shift-Enter. And now, so we get this really tiny p-value, 5.7 times 10 to the negative 62nd. Okay, so definitely there's a difference, and just looking at them, you know, we saw 1.4s and 4.7s and so forth. They looked very different. Now, commit that p-value to memory, right, because I also have an analysis of variance here where I went ahead and already put the data in. So there's all those same data in an analysis of variance. And here's the p-value. Can you all see that? No, you can't see that. Well, let me, there we go. Now you really can't see it. 5.717 times 10 to the negative 62nd. My favorite number. Okay, there it is, right? Same p-value. Now, also notice, here are the two means, 1.464. Okay, remember that number, my second favorite number. Right? We go back to the regression. Look at the intercept, 1.464. If I move the mouse so you can see it. Same number. Okay, so what happened was the dummy variable that was a 0, that's its mean, its average was the y-intercept. Okay, now let's take that y-intercept, that average, and add to it our slope. Hit enter, 4.26. See, this is exciting. You might not believe me, but it is. Look, 4.26, the mean of the other. And so what we find when we do this is that we can use the linear regression, and we get a model this way using the dummy variables. Okay, we get a model y equal bx plus a, where a is equal to the mean of A, category A, and B, the slope, is equal to the average of B minus the average of A. And the p-values are the same. Now, look at the null hypothesis, right? Remember, here's the null hypothesis is that the average of A equals the average of B. Our null hypothesis for regression is that this little b equals 0. Right? So H0, b equals 0. But what's b? It's just b minus A is equal to 0, but I can write that as the mean of A equals the mean of B. They're the same exact hypothesis. And they're both assuming normal distributions and so forth. So we end up with exactly the same p-value. So if I have an analysis of variance situation, at least right now in this chapter, with just two categories, I can set it up with these dummy variables and just run it in the regression and get the same results. Okay? Now, I think that's pretty exciting, but it's not just wait till the next chapter. You will be floored. You are so excited about what you can do with this. Okay? So you have to wait till the next chapter, but you will be very excited. Okay. So that is the regression and how we can actually go ahead and just do an analysis of variance. Or, other way around. Is if we had an analysis of variance, we could just do it with regression. And again, where this is going to be helpful is in the next chapter when we go to multiple regression, we can actually just start looking at all our variables at once. Confounding variables as well as our explanatory and response variables. All righty, so I guess I'll see you next Thursday then.